I'd like to introduce our first speaker, Adam Brandt. He's an assistant professor of energy resources engineering at Stanford, and he's also the principal investigator conducting carbon capture systems analysis as part of GSEP. It's called Comparing Exergy Efficiency and Electricity Costs of Various Technology Options. Overall, his research focuses on reducing the greenhouse gas impacts of energy production and consumption, with a particular focus on fossil energy systems. His research includes life cycle assessment of petroleum production and natural gas extraction, particularly related to unconventional fossil fuels such as oil sands, oil shale, and hydraulically fractured oil and gas resources. He also is a specialist in computational optimization of emissions mitigation technologies, and he came to us after completing his PhD at UC Berkeley. So please join me in welcoming Adam Brandt.
Thanks. All right, so thank you, Sally. Thanks for inviting me to speak, and thank you everyone in the audience for coming to hear this talk. This is fun for me because this is a chance to talk about some research that I've been working on for the last 3 years with a couple of my students, Stuart Sweeney-Spith and Yuchi Soon, and also with able co-PI in the form of Chris Edwards. We're going to touch on some thermodynamics in this. If any of you know Chris, you will know where to lay the blame for any mistakes in thermodynamics. Hint, it's not with him, it's probably with me. Just some motivation for what we're thinking about here. Applying CCS at scale, that is at the sort of gigaton scale to mitigate CO2 emissions or mitigate climate damage, would almost certainly require economy-wide shifts in material and energy flows. This is the case because massive amounts of material are moved in our fossil energy system. Obviously, designs for CO2 capture equipment should minimize capital investment, minimize material consumption, and perhaps most importantly, minimize the energy penalties associated with the separation and storage of CO2. Importantly, we also want to avoid unintended consequences, maybe framed as backfire, elsewhere in the economy or biosphere. That is, we don't want to institute large-scale changes over the course of decades and then discover that there are sort of secondary or ancillary side effects that we weren't aware of. So therefore, to meet these goals, I believe that properly assessing CCS technologies requires, one, understanding economy-wide environmental impacts, and two, being able to compare diverse environmental outcomes across different media and different timescales. And our analysis here, although it's applied to CCS, we think is a pretty groundbreaking new approach to basically satisfy both of these goals for a technology. So as far as goal one, in terms of achieving an economy-wide perspective, the methodology we're going to use is called life cycle assessment. So life cycle assessment is a technique that's been under development for some decades to model economy-wide environmental impacts from a technology by tracking flows of natural resources and pollutants transfer between the economy and the ecosystem. So here we've got an example supply chain here on the left where we have, for example, a coal mine that's sent into a coal transport system, let's say via rail, and then to a power plant. This supply chain sort of spiders out, and for example, we have diesel fuel, steel, and lubricants are consumed in coal transport, and to make steel, we needed to input iron, ore, and coal. You'll note there that this chain has fed back on itself. Only 2 orders were moved from sort of the initial supply chain. It's actually a little problematic that the term supply chain has entered the popular sort of terminology or sort of popular mindset, because all of these chains mathematically are much more akin to supply sort of webs that feed back on themselves, and mathematically you can show that that's the case, quite profoundly self-interact. So goal 2, we want to compare diverse environmental impacts. So sort of goal 1 was saying, let's cast our net across the entire economy. Goal 2 is to compare diverse environmental impacts. We need to think about, is this resource going to have impacts on water versus air? Is this resource or this technology going to have impacts now or in the future? Is this going to have, for example, chronic or acute health or ecosystem impacts, right? And so there's lots of dimensions along which environmental impacts can vary, and trying to quantitatively and rigorously compare and value these is a decades-old problem in the world of environmental assessment. Many schemes have been proposed. There's probably 5 of them in common use, mostly in Europe for regulatory purposes for product manufacturing standards and sustainability standards. There's a variety of schemes proposed. I would say the generous way to put it is that consensus is lacking. It's actually really hard to rigorously understand how you should trade these things off. We have a project with the Woods Institute in collaboration with just as an example, in collaboration with a civil engineering professor, where we're looking at co-minimizing energy use and toxic byproduct formation from MEA-based capture systems, because as it turns out, monoethanolamine-based capture can release highly carcinogenic nitrosamine compounds into watersheds nearby the power plant, right? And so this is this water versus air sort of trade-off. Exergy for at least 30 years, and I'm sure before that, has been proposed as a unifying thermodynamic measure of potential harm from effluents. I would say my perspective is that Exergy is likely the only contender out there for a sort of a unified scientific approach to rigorously comparing these. And it has many virtues, and this has literally been discussed, as I said, for decades. It's not clear that all the issues have been solved, but to me, it's really where the action probably is. Just to explain a little bit about Exergy. Exergy is, you can think about it in many ways, one of which is the maximum work that can be extracted from a system, a thermodynamic system, where the system contains something that you might call a resource, which is out of equilibrium with an environment or a reference environment. Okay, so in this case, the resource could be a natural resource such as coal, or it could be a waste stream that is out of equilibrium with the environment. It's a measure of the potential for change as the resource equilibrates with the assumed unchanging sort of background environment. It's also the useful part of energy. Another sort of unfortunate set of terminology is that when most people in sort of common parlance talk about energy, almost always what they're actually talking about is exergy, because that's the sort of stuff that you can use up. My car is out of energy, I don't have any energy, right? That's the useful part of energy is what we actually care about. And we all know that the total quantity of energy is actually conserved, while exergy isn't. Exergy comes in various flavors and is variable depending on the nature of the disequilibrium between the resource and the environment. If the resource is higher than your reference environment, then your resource contains gravitational potential exergy, and so on. So the exergy content of flows can be envisioned in this way. We can define something called a process, which is here just sort of this gray box here. The process takes in two forms of flows. It can take in natural resources from the environment. We have our environment up here in the upper left. And it can take in other inputs from other parts of the economy. Each of these mass flows can have some temperature, pressure, Gibbs free energy of formation, molar concentration, elevation and velocity, things like this. And you can use those terms to basically, here on the right, I'm obviously not going to go over the equations, but you can basically use those terms to compare the various forms of exergy that these inputs have relative to the reference environment. The process then spits out two types of products, one of which are wastes here on the top. Those go back towards the environment, and the other is the product output, which is then traded elsewhere in the economy or used in other economic processes. Okay? So for our sort of conception here, a process is something that takes in exergy in the form of natural resources and other products and outputs exergy in the form of products and wastes. The outputs are always strictly less than or equal to the inputs, actually strictly less than in a real system, because all real processes destroy exergy. So methods, so in order to integrate these two perspectives, we wanted to generate an economy-wide exergy model. We used something called the EcoInvent Lifecycle Analysis Dataset. It's a product of the early 90s from the Swiss ETH system that's since been spun out. It's a connected set of physical flows between 10,000 different processes representing the global economy and 1,700 flows of waste and resources coming into the economy from the environment, waste coming out of the economy into the environment. So you can see here sort of this conception on the left, or on the upper right. We have the ecosphere out here. We have the technosphere, where process one is pulling some natural resources from the ecosphere and emitting some waste. Those resources are processed and sent through sub-processes or sort of downstream processes, all of which emit some waste to the environment. These two approaches have never been unified before because it's actually fairly complex. You need it to have a lot of information to compute the exergy of a flow, and these data sets are very complicated. A big advance developed by my student Stuart was a way to basically pre-analyze, in this 10,000 by 10,000 process model of the economy, pre-analyze analog technologies, sort the impacts by their magnitude or their potential magnitude, and basically filter them so we actually only need to compute exergy for a relatively small number of processes, hundreds rather than tens of thousands. And after that, we generated an exergy conversion matrix, which has very detailed sort of exergy values or exergy intensities for some flows. But the vast majority of flows, and this is not to scale, the vast majority of flows are modeled as sort of average, typical stuff. Interestingly, the industrial metabolism metaphor, if you guys heard that, is surprisingly accurate. If you look at, you sort of look at the results for demanding something from the economy from this model, what the economy does is basically take in carbon, take in minerals, and take in air, and emit to first order warm, slightly warm wastewater with slightly higher concentrations of some elements in it, and breathes out warm CO2 containing exhaust. And to first order, this looks like something an organism would do. And so we can get something like 99.99999% of the mass flow with the top few hundred processes, because really that's kind of what the economy does. My student Yuchi Soon took over from Stuart to analyze a baseline CCS system. He analyzed the NETL baseline CCS system from the National Energy Technology Lab. We modeled and sized all the reactors in great detail to generate a really detailed materials bill. Here's the flow, the sort of process diagram from the DOE report. Here's our end result. Using basically chemical engineering models to sort of size and parameterize the reactors. And we tried to make this sort of equal to the standard NETL plant, because this is commonly used in the CCS world. So just some results. So this is the baseline system. This is the baseline NETL system without CO2 capture. So this is just normal coal. Over the life of the planet, takes in about 1,300 petajoules of natural resource exergy. Most of this, the vast majority of this, is in the form of chemical exergy of coal, but also exergy of ores, iron ores to make steel, and other input materials. This exergy is then partitioned into three categories. Output electricity that we care about, that's the yellow bar, that's the sort of final product. The exergy content of waste flows, right, the things it's putting out in the environment, and then a very large term of exergy destruction. Again, this is not a an ideal or reversible process, so there is exergy destruction involved. We're now going to attach the CCS system to it. What we see here is the required inputs of natural resource exergy increase significantly. The electric output stays the same because it's been normalized, and the waste bar here on the right, in the case with CCS, only drops slightly. The at plant higher heating value efficiency reported in the NETL baseline for coal was about 37%, dropping to about 26% when we add CCS. Taking an economy-wide exergy efficiency, and what this means is this is the exergy content of the electricity sold by the plant, okay? The plant gate, or sort of the bus bar where it interacts with the grid, divided by the exergy content of all natural resources brought into the plant, right, directly in the form of coal, indirectly in the form of iron ore and everything else that was required to build and operate that plant. And you can see these economy-wide exergy efficiencies drop to 23 and 17% when you go to without and with CCS. And in fact, we had to expend 50 units of natural resource exergy for every unit of pollution reduced. This is where we were as of a few months ago, 3 to 6 months ago, and this is not a very encouraging result. We decided to dig into what was happening here. As it turns out, huge amounts of more material, including 12 million tons of coal over the life of the plant, need to be consumed additionally in the CCS system than the non-CCS system, which results in parasitic emission of CO2 elsewhere in the economy that claws back some of the benefit of capture, and also results in additional waste heat emissions to water and air, and additional other air pollution than CCS. But that's not the whole story, and I don't actually think this is the real story. Exergy actually measures disequilibrium of a resource with an unchanging reference environment. So the mental model here is you've got some resource, right, and it's interacting with some reference environment. It can interact chemically, let's say oxidize and form a reference species. It can dissipate out into the atmosphere, right? And eventually it doesn't change the reference environment, but it's essentially been lowered thermodynamically down to this equilibrium condition, this unchanging condition. This is a really poor model of what we actually care about for CO2. CO2 builds up over centuries and changes the reference environment. Current CO2 emissions around the planet are around 1,000 metric tons per second, day in, day out. Over a century, this has caused the effective reference environment to change. This changes the energy balance of Earth's highly driven, highly non-equilibrium climate system. The Earth, as it stands now, is massively, massively thermodynamically uphill. Right? And this is the way I think about it. I don't know if that's the right term. Chris could probably specify that more carefully. That is, an alien sitting in his spaceship at the edge of the solar system could look at the Earth and they would say, something funny is going on here. There's lots of oxygen, there's lots of other stuff that we wouldn't expect if this system were sort of in a long-term thermodynamic equilibrium. All that oxygen would be sucked up, forming mineral and metal oxides, forming CO2. It'd look much closer to Mars or Venus, right? And so Earth is this sort of thermodynamically, it's not in its ground state. Also, CO2 affects ecosystems, and it's really not clear that exergy is the right way to think about that. So we're proposing, and this is where if I'm going to go off the rails, this is where I'll go off the rails. And so Chris hasn't seen this stuff yet, and he's my thermodynamics guru. So I'm just a brown belt, and he's the sort of the samurai master. So he can offer some advice here. I'm proposing augmenting this with a time-integrated exergetic impact. What I'm going to do here is highly first order, because this is sort of a non-equilibrium thermodynamics problem of possibly the most challenging type you could ever imagine. And so all I can do here, right, the climate system is incredibly complex. All I'm doing here is sort of a first order approach. Let's imagine sort of two worlds and compare them, and these worlds evolve over time. On the left-hand side, we've got sort of our cartoon world here. This is the world without emissions. We've got some energy coming in from the atmosphere. And on the right, world B, we have world with emissions, okay? And the difference between these two worlds is that the energy input from the environment to the biosystems and human systems that we care about is larger because of the increased thermal energy transfer and increased radiation from the atmosphere. Zhang and Caldera quantified this. Caldera's Ken here from the Carnegie Institute. Quantified this with a coupled climate and ocean model, where they were able to run these coupled models for thousands of years. And they said every mole of CO2 results in 4.5 times 10 to the 10th joules of total warming. Compare this to the heating value of pure carbon, or the energy of formation of pure carbon. It's about 114,000 times more than the energy content of the coal, or oxidizing the carbon. This is quite a problematic result. So for a first estimate of the sort of time-integrated exergetic impact, this is not actually an empty slide. It may look like it. Down here on the left is the graph I just showed you 3 or 4 slides ago. You will see that I shrunk that down for a reason. If we add again, extremely first order quality adjusting factor to this additional heat input, to the biosphere and the human system, and here I assumed an average delta T of 1.5 K over the life of the CO2 molecule. It's about 600 times, basically the difference in waste inputs, or the waste inputs to the environment between these two worlds is about 600 times the exergy that we would consume in capturing CO2. Okay? So from this perspective, this sort of time-integrated perspective, investing some natural resource exergy and capturing the CO2 looks like a fabulous deal, right? Because we're driving the climate system, we're driving the biosystems, we're driving the future human societies thermodynamically much less than what we have to spend. You might say, does the thermodynamic quality of environmental impacts matter? Why did I adjust Caldera's factor of 100,000 for thermodynamic quality? Why didn't I just use 100,000? To illustrate this, and this is maybe where we'll get a little controversial, but I think this is a fun thought experiment. These are illustrations of 2 things that are happening around the planet right now as we speak. On the left, we have lightning. Negative charges almost always, although not entirely. Typically, negative charges will build up on the bottom of thunderclouds. Effectively store energy in an electrostatic field between the ground and the sky. When that potential crosses the tens to hundreds of millions of volts, you begin to rip apart air. Air starts to ionize. And you basically form a channel of plasma or ionized air, and then all of a sudden, in a split second, this charge balance, or this energy stored in an electrostatic field, dissipates. Satellites find that you have about 45 to 55 or 50 flashes per second around the planet average from lightning. About 80% of those are cloud-to-cloud or intra-cloud flashes equalizing the static charge within clouds. About 20% of those hit the ground that we know about. Each flash dissipates on order 1 gigajoule, so if we say 10 per second times 1 gigajoule is 10 to the 10th watts. Fun, right? So that's effectively the amount of electric potential that's being sort of dissipated or equilibrated at all times on the planet on average. Case B, and again, these are two things that are actually happening right now. Case B, we see that radiative forcing due to CO2, according to AR5, is about 1.68 watts per meter squared, measured at the tropopause per unit meter squared of the Earth's surface. The area of the Earth is 5.1 times 10 to the 4th meter squared, so this power is of the order 10 to 15 watts. I'm not a social scientist, but I think if you went out and asked the public, how many of you believe in the existence of lightning? Almost everyone would say yes. How many of you believe in the existence of climate change? You get a lot of no's, despite the fact that the effective energy flux due to climate change is 10 to the 5th times larger than the constant energy flux due to lightning around the entire planet. Okay, so if you can imagine a bizarre alternate world where instead of affecting the radiative balance of the atmosphere, CO2 caused charge to build up on clouds. In order to dissipate that charge, the lightning on the planet would need to increase by a factor of 100,000 to dissipate this charge. Again, I'm not a social scientist. I think in that world we would not be having an argument about whether or not climate change is real, okay? So again, quality matters. Lightning is about as spatially dense, temporally dense, and exergetic, has a high exergetic quality factor as you can possibly imagine. The opposite is the case with radiation from climate change. It's unclear how to measure CO2 impacts on biosystems, and I'm out of time, but I will slide into home here. Chemical exergy is a poor indicator of biological impacts. Sodium cyanide has a chemical exergy of 13.7 megajoules per kilogram, while canola oil has a chemical exergy of 40.6 megajoules per kilogram. The lethal dose of sodium cyanide is 200 to 300 milligrams and will kill you very quickly. I don't know what the lethal dose of canola oil is. Too much of anything will kill you, but given by how many French fries my children will eat if you put them in front of them, the lethal dose for canola oil is much larger than 200 milligrams. Or myself, I am known to enjoy French fries. Well, various methods have been used to understand the thermodynamics of biology and basically value from a thermodynamic sense the incredible order and in a sense the incredible sort of thermodynamic improbability of life existing. They'll do this, for example, by analyzing the information content of DNA strands and coming up with a multiple to the sort of energy value of just the fats and carbohydrates and proteins that we're made of. I don't know that I believe this, and I don't know that exergy is the right way to measure impacts on biosystems, but we know the answer isn't zero, so we shouldn't ignore it, right? So any unified indicator should do something about this. So some conclusions. Holistic environmental assessment of new energy technologies is possible. You can cover all processes of the economy and measure impacts on a consistent thermodynamic basis. So this is really cool. I'm very excited about this. Traditional exergy analysis that people have proposed for 30 years of CO2 makes the benefit of CCS look small. Extended impact analysis that looks at changes to this sort of driven climate system that we have makes CO2 look like a wonderful deal, or CO2 capture look like a wonderful thing to do. And the thermodynamic quality of environmental impacts does matter. I think there are numerous applications of this system scale thermodynamic analysis for comparisons of other energy technologies. For example, we could look at solar panels and all sorts of things. So lots of fun stuff to do here. So thank you, and I'll take any questions you may have.
A quick clarifying question. So 10 to the 15th watts of lifetime radiation for all the carbon burned and released that's sitting up in the atmosphere over the 5 times 10 to the, I missed that last, 10 to the 14th meter squared. Is there a translation that you've done as to total lifetime radiative forcing per meter squared for an individual carbon molecule?
That's essentially what Caldera and Zhang did. And that's where they got this time integrated 100,000 times heat input, right? And so what they did basically is they ran a coupled, it's a very challenging problem to do actually. This is sort of why it hadn't been done before, but they ran a coupled oceans model, right? And modeling the chemical equilibriums in the oceans, and the uptake is in carbonate and bicarbonate, the eventual settling out of CO2 to form rocks and minerals and things like this, coupled with a climate model, ran it over very long time periods, thousands of years until the model equilibrates and removes all the CO2, and they get the time integrated heat impact of 100,000 times the heating value of the coal. The point of the quality adjustment is that you can't just say 100,000 times the heating value of the coal, because you burn coal and you create very high quality heat, right? And then, whereas what's coming back to us is this very gentle sort of, it's still energy and it's a hell of a lot of energy, but it comes back to us at a very low quality gradient. I think to do this right, it would require my sort of back of the envelope, you'd have to expand it. So there's been some nice observational evidence in the last 6 months of changes in the what's called the downwelling long wave radiation due to CO2 enhancements. And so they're seen around the 12 to 13 micron, the edges of the main CO2 band. You're seeing more back radiation. And this is the first really solid experimental evidence that's published in Nature of the sort of the ground level forcing effect of CO2. So some of this is coming at us as heat, some of this is coming at us as 12 or 14 micron infrared radiation. I would need to work with an atmospheric physicist or atmospheric chemist to do this right. But to first order, I just modeled it as heat so we could talk about it. But taking this 100,000 at face value effectively assumes that those qualities are equal, and they're not. They can't drive as much change. Yeah.
I'm a retired engineer for decades, so
Okay.
you're speaking to a layman.
Sure.
I was having trouble following this in terms of some of the statements as I think I understood them.
Okay.
And the conclusion. I think you said something, you're talking about the difficulty of measuring the impacts on the Earth of the climate change. I think that you were talking about that thermodynamically and chemically. Sure. Did I get that right?
Sure, yeah.
Okay, and then you concluded at the end that CCS was unlikely to have any important impact on climate change, if I understood that statement correctly.
So that was
and I didn't follow any connection there.
Yeah, so sorry, let me back up. The conclusion of the first half of the talk, using the methodologies that people have proposed for 30 years, this sort of standard exergy analysis, is that there's not that much benefit to sequestering CO2, because CO2 does not have that much exergy content relative to the atmosphere. That is this very static, bring the exhaust to equilibrium, dilute it out in the atmosphere, how much driving potential is there? That's a very sort of static, traditional, sort of simplified mental model for computing exergy. In reality, we know that many of the assumptions buried in exergy analysis don't work for CO2, like the idea that it doesn't build up, or that your reference environment is always unchanging. We actually know that's the whole problem with CO2, is that the reference environment is not unchanging, right? And since 1750, we've added a lot of CO2 to the system. It's very stable over a long time period.
Most greatest interest to me is what led you to the conclusion that CCS was unlikely to have any important impact?
Yeah. So that's not my conclusion. That's the conclusion that how people have been saying you should do this. You run those numbers, CCS doesn't look beneficial. You run the numbers taking into account this heat input that happens over centuries and quality adjusting it, and you get, this is the red waste, which was the bad bar in our old graph. You now add this enormous, which dwarfs the size of the original graph, basically. And so you get a 600 times return. Every unit of exergy you invest in scrubbing CO2, you avoid 600 times that amount of thermodynamic pollution, so to speak. So CCS looks bad from the first perspective, like the best deal we could possibly imagine from the second perspective. It looks fabulous. Hugely important to do CCS if you believe this broader perspective, which I do.
I got it.
Yeah.
There was one other question, though. There was something like you spend 50 times the amount of resources for one unit of benefit.
Yeah.
On waste.
That's using the more narrow boundary, not looking at CO2 impact over time. And so that's saying the amount of natural resources you have to expend, and almost all of this is extra coal because of the inefficiency of the plant, doesn't lower your waste outputs very much. And so you don't get much quote unquote sort of reduction in the environmental drive. And then what I'm saying in sort of the second half is that actually when you do the right size of that red wedge that we're concerned about, the red bar, it's actually huge, and that's actually the whole rub of moving to a broader sort of thermodynamic assessment.
I've got
over
it. Thank
time.
you very much.
Yeah, sorry about that. That was, yeah. And I think we've got maybe a minute, so maybe one more.
I got the microphone over here.
Oh, yep.
So I'm thinking biochar. You talked about essentially modeling, and it seems like this would be a really good candidate for a geographic information system based model of all economic activity plus all the background stuff. And that number there, I mean, you could reasonably show if everybody does some gardening work and buries some biochar the way they were doing in the Amazon 500 years ago, we could take geologic quantities of CO2 out of the atmosphere, and then you're saying that it's worth 600 times the amount of work that's done to do that. So that could be a really nice teaching tool, as well as a nice economic modeling and planning tool for the planet.
This would be the right way to do biochar, because it interacts with all sorts of other agricultural systems and trucking and all these things you might have to do to do biochar at scale. So this is exactly what you'd want to do to analyze biochar. And I think the benefits would be the same or larger.
You wouldn't need the trucking because you'd be doing it on a local basis as you farm and grow trees.
Sure, and you could model both cases, and yeah. But this would be the right way to do biochar. And people have started on that, but I think this approach is better. I think I'm done. All right. Thanks, Sally, and thank you, everyone. Feel free to find me afterwards for questions.